Okay. Yeah. Okay. Welcome to week 5. I'm recording now. So today, like I said earlier, you may not be learning a lot of new like physical tools in Fusion. I don't think we're opening Fusion today. But I'm going to be talking a lot about how you might want to design things. So I'm it's a lot about like design practices, good design practices and features whenever you make stuff. Um, and the main goal is for you to be thinking about these as you go in and start designing your final projects. So I'm going to reintroduce the final project to you all today. A lot of you kind of know what's going on because I mentioned it a couple times. Um, I hope you now have the knowledge to make your final projects today if you really wanted to. And once we review like the requirements, now that you know how to do a lot of these things, you'll see that the requirements for this final are pretty lax. So I don't want to stress you all out too much. I know you have exams and stuff to prepare for. I actually have a fluids exam next week on Monday. So I'm trying to figure out what I'm going to do because I can't exactly be in two places at once. So I'm going to see what I can do about that. Hopefully we can either have class on another day or I can move my exam, but we'll see if the professors are nice. But yeah, anyways, today is a lot about design choices, and then we're going to be dabbling in the 3D printing part. If you saw earlier on the spreadsheet, we're like really close to that 90% for last week on attendance. So again, please fill out the forms if you haven't already, because you guys can make me broke and I can buy you food. And yeah, I'd be happy to do that. I haven't had the opportunity to buy food for everyone yet, so I'm really hoping this semester is the semester that it happens. They're really close. Yeah, let's just get into it. Again, I'm going to be talking a lot, but I hope you at least hear or absorb some of what I'm going to say. Um, yeah, starting with the final project, you've probably seen this slide a couple times already, but your final project is basically a free-for-all. You can design anything you want. Obviously, please make it school appropriate. Um, and then please don't make it something that we already did in class. It's kind of self-explanatory. So don't do like the engineering fountain or something else like that we've done already. And then the other requirement is that it must contain more than 5 design features. So a design feature would be something like an extrude or like a revolve or a chamfer or a fillet, right? So 5 design features is actually like pretty low. So you'll see like even for like the hammer, we did two design features already, right? And for some other things like the hair dryer and stuff, we did probably close to 5, if not more. So 5 is pretty lax. Again, like I don't really have control over what you submit for your finals. So if you're like really in a bind and you have like 8 million exams that you have to take and you just need to crank it something out, you can do that. But you've seen from some of the other slides, I think it's here. Yeah. Like some people spend a lot of time on this. And then they create some really awesome stuff. I really enjoy when I see these, but I totally understand if you're in a bind and you just need to turn something in. Just please turn something in because like this final is worth 90 points. And with these like really lax like requirements to get these points, like it's not that bad. So just turn something in, even if you're busy, and you probably will pass if you've been turning things in and following along. The last point is you want to design this final with manufacturability in mind. This is something that we've added over like recently in past few sessions. And it's because in the past, if you're unaware, I do print all of your finals. So if you give me a design that looks super cool, but like it's super tiny or it's like not really printable, then I'll be like, you'll like come and like get your final model and then I'll like hand you like a pile of like filament, right? And then you'll be sad and then I'll be sad because you won't really have anything cool to show from this class. Um, so that's why we're having this presentation today, because I want all of you to have really successful and really awesome final projects. Um, I'm going to be talking about like bridging and overhangs and stuff like that for 3D printing. I have had people, I like bridging is like kind of a no-no when it comes to 3D prints. Uh, and we were like, yeah, please don't like have really large bridges. And then someone submitted like a Golden Gate Bridge for their final, and then it like crumbled to pieces, and we're all sad. So please don't be that person. If I see it before I print it, I might reach out to you. Or if you have questions on your design, be like, hey, like, is this printable? Like, should I change something? Like, feel free to like send me a picture and I can take a look. Again, I want these to be really nice. Like, maybe you put it on your desk for like a fun desk toy or whatever. But I would like them to be printable for both your sake, so you can learn how to do it well, and for my sake, so I have an easier time printing stuff. So yeah, that's what we're going to be mainly talking about today. Does anyone have any questions before we go into it?
Are there any like dimensional limits?
Okay, that's a good question. I like to leave it like pretty open. My answer for that is usually just be reasonable. Because again, there's a lot of you, and I only have like a couple printers. They are fast, but like, please don't make something like this big and like takes me like a couple days to print, because I want to make sure everyone gets their finals. Usually like around like the size of your hand is like a good area to be in. I'm like, it's kind of hard for me to give like exact dimensions because some people like to make things that are super tall and some people like to make things that are really flat. So I get people like, for some reason the Saturn V rocket is a really popular final project. I've gotten like 4 or 5 of them. So that's like, obviously the footprint is like tiny because it's a rocket, but then it's super tall, right? But then I get people who print like license plates and stuff. So like it's kind of a big mix. I just, you are all smart. I'll trust your judgment. If something is too big, I'll probably scale it to size. If it looks like dimensionally important, I might like talk to you before, or you can ask me if it has to be dimensionally accurate. Um, but yeah, I'm pretty flexible. Well, that's something we're gonna be talking about today. So, it's pretty fun. I should have brought some samples. I forgot, but yeah. Um, yeah, any other questions? All right, sick. So, designing for manufacturing. A lot of people simplify this for as like DFM, so design for manufacturing, if you didn't know. But anyways, there's multiple kinds of manufacturing. One of the things that you might think about more traditionally is something that we call subtractive manufacturing. It is usually you take a block or some kind of a material and then you cut away at it until you get the product that you're after, right? So this can be anything from like drilling a hole into something to like turning it on a lathe or using a laser cutter or water jet. Those are all subtractive processes. Like you're cutting things away. You can see like left to right starts as like a block, and then you get this profile. You can see here there's like a bunch of different processes. Drilling and milling, along with turning, are something that you might be thinking about. But stuff like grinding and stuff is technically subtractive as well. That's me being super safe and cutting a metal tube on top of totally not flammable objects. But yeah, these are all subtractive processes. They can get pretty expensive just because you need to start out with more material than you actually need for the part. And then depending on the precision, it can get pretty expensive too. So like milling machines and stuff like that are awesome. If you've been to the ME machine shop, we have a couple. But like, those machines can cost like tens of thousands to hundreds of thousands. So typically like drilling and milling machines, well, like a drill press is like somewhat accessible. But like the high precision like milling and blades, mills and lathes are typically out of reach to like the personal like a student, unless you like go to the machine shop, right? But it's not like you have one in your garage. If you do, you're like really lucky, and I have some friends who have that, but I don't. So it's awesome. I could talk about these for forever, but we're mainly going to be talking about 3D printing because that's most relevant for us students. And that's what you would call additive manufacturing. So you start with nothing, or at least like a base plate or something. You'll add material with some kind of tool to slowly build up your final product. Um, so typically when people talk about additive manufacturing, you think 3D printing, but injection molding is also an additive process. So these kind of fall under very similar like requirements, which is why 3D printing does benefit a lot from the injection molding um, like style of machining or making parts. You get a lot of like the material benefits from all the research from injection molding because it's been around for so long, and it's starting to trickle down into 3D printing. But yeah, injection molding is also really expensive because you have to like pay hundreds of thousands for like molds to make one part. So we're not really going to be talking about it. So we're doing 3D printing. It's pretty awesome because you can make really complex parts with zero tooling. And when I say zero tooling, like you can see here, like there's these really complex like machine channels in this like injection molding part. Just so you can, inject the material inside to get your part, right? That tooling is really expensive and out of reach for normal people like us. But 3D printing, you don't need that. You just have the machine and it can do like basically whatever you want. It's pretty awesome. I've been doing it for a while. It's definitely become a lot more mainstream. So yeah. Anyways, plenty of applications for 3D printing here. Everything from rapid prototyping to full on like house production, which is pretty cool. I'm not going to go over all of these, but it's making its way into so many industries just because of how cost effective it is, and you know how you can get really complex geometry for low cost. So yeah. Anyways, there's a couple different kinds of 3D printing. I'm not going to go over all of them, but SLS and SLA are two pretty popular methods, not as popular as the last one. SLS, you basically take a powder and you use a laser, and it shoots the laser and melts the powder, and then you add more powder on top. And you keep on doing that until you get your part. It's pretty awesome. They're pretty strong. You can do like SLS nylon, pretty nice materials. There's also SLM, which I haven't listed here, but it's basically that process, but for metal. So they use metal powder. It's also pretty awesome, but it's typically more expensive and kind of out of reach to consumers again. So you'll typically see something like SLA or FDM, which we're going to talk about in a second. SLA is kind of similar to SLS, but it's like upside down. It uses a vat of resin, and then it uses like a special UV display. So it's basically like a TV that shines UV light. So you can get a really accurate profile, and then it builds it up. Like it shines a light, moves up a little bit, shines some more light till you get your part. Resin printers are pretty cool. You get really high detail. Sometimes the parts are a little brittle, but the materials for this are getting better and better all the time. But yeah, the main thing that we're going to be talking about, which is something that you might be familiar with, is FDM or FFF printing. FDM is technically like a trademarked like name or something. So you'll kind of see these like FDM and FFF used like interchangeably. But yeah, it's basically the same thing. The concept is you take some kind of material, you heat it up, push it through a nozzle like this. It's basically, I like to think of it as like a fancy hot glue gun, but attached to a robot, right? So this robot precisely controls how much material you're depositing and then where you're depositing it. And it'll move around, creating your profile and building up your part, right? So yeah, that's basically how 3D printing works. I'm sure a lot of you have seen a 3D printer at this point, but if you were curious how it works. But there's a bunch of different settings that you can change while 3D printing stuff. I don't know if you've messed with like the DPI setting on your printer when you print stuff, but like DPI stands for like dots per inch, and you can change like how good the resolution of your 2D printer is if you change the DPI. But with a 3D printer, because you're working in 3D space, you have so many more parameters to change. So I'm just going to go over a couple of them today that I think are pretty relevant, but you'll see soon that there's like a bajillion different things that you can mess with. But to start, there's layer height. It's probably the first thing that you might go to change. But typically, once you kind of get a profile you like, you don't really change it. But it affects the time like probably the most out of all of them. But it's basically changing how coarse the layers are, right? So for the 3D printing process, again, it slices your model into a bunch of sections and then it prints like a 2D profile of what it sees, right? So when it slices it, you can change how coarse it is. And when you do that, it can affect the printing time. Just because if you have more layers, there's more places for your printer to move and it'll take more time, right? But if you have less layers, less movement, less time. But you do get some trade-offs, right? The more layers you have, the more precise your resolution is in the Z direction. So you can see here, like on the 0.8 side, it's very coarse. You can see the layer lines. But then if you go finer and finer to like 0.1, it becomes like a lot harder to tell, right? So depending on what you're doing, this might be important to you. Like if you want something printed really fast, like you probably want a coarser layer height. If you want something to look super, super nice and like almost unrecognizably 3D printed, you could probably go super fine, right? One drawback to printing super fine is that the parts are technically weaker, because one of the main failure points for 3D printed parts is like one of the layers shearing from another one in like the Z direction. So every time like the layer makes a bond here, it's slightly weaker than the actual material itself. So if you print it apart and you hold it in this direction, it will probably break. And if you have more layers, then it'll typically get weaker. So for really strong parts, you might want to print at a coarser layer height. But we're kind of splitting hairs here. But it's something to know. You can see like the arrows up and down. Increasing in layer height increases your speed. You'll get the part faster. It reduces surface finish. It's not as strong, but opposite is true if you make the layer height smaller. Yeah. So perimeters are just perimeters, basically how thick the outside of your print is. If you didn't know, a majority of 3D printed parts are actually hollow, just because like you don't actually need the part to be solid to do its job. And most of the strength comes from the outside. So even if the inside was completely hollow, as long as you have a good wall thickness, you'll get most of your strength through that. So if you're looking for a stronger part, I typically recommend you increase the perimeters before the infill, which we'll talk about in a little bit. But the perimeters, they usually count by like the number of passes. So it usually goes by your nozzle diameter. So the standard nozzle diameter right now is 0.4. So you can see here, there's two lines here. So two perimeters times 0.4 means like this wall thickness is 0.8 millimeters wide. But as you increase the wall thickness, it gets thicker and thicker, it gets stronger. Again, if you increase your perimeters too much, you're going to be wasting time and sometimes material if you're making it stronger than it needs to be. But again, there's drawbacks. So typically for like desk toy stuff, you don't really need like a high number of perimeters. Like typically like 2 or 3 is fine. But if you want like a super strong part, typically you want to increase your perimeters. Yeah. Again, these are all just like pros and cons. It's very specific to your application, but it's something to keep in mind. The infill, which I just mentioned earlier, is basically how dense the part is on the inside. So you can increase or decrease that to save time or make it stronger. Again, I typically recommend perimeters before infill, but having a good balance is good. So I think the standard is usually typically like 3 perimeters, 15 or 20% infill. But when I want to print stronger parts, I can go like 4 perimeters, 5 perimeters at like 25% infill. That's just personal preference, but yeah, again, more infill means more time, more cost, but might be a little bit stronger, right? So again, I'm just going to be rambling. This is all like kind of self-explanatory, but it's something to keep in mind. For supports, you'll sometimes encounter situations where your printer or you import a geometry to print something that is physically impossible for the printer to replicate. So for FDM printing, like you typically can't print things out of like in thin air because there's gravity and things will droop, right? So sometimes we'll add like a sacrificial material. So you can see here, like this gray is like support material that you have to print. So this part can lay on top. If you didn't have that, then your printer would try to print it, and then all the material would just droop, and you'll be sad, and the print won't really look like what you wanted. So you can add supports like this. Obviously you're adding more material and it's sacrificial material, so it's waste. So as a designer, you typically can design things to not require supports, right? So one of my challenges for you when you're making your finals is to try to limit the amount of supports you need. Most of the finals I get don't need them at all. So if you design things properly, you may not need it. Obviously, if your geometry has to be a certain way and you need supports, like you're just gonna have to use it. But because you have the power to design things, you can try to design them out. And I'll be talking about little tips and tricks to maybe reduce the amount of supports that you might need with your models. But yeah, does anyone have any questions? I know I'm just like rambling, but I hope this makes sense to you all. All right, sweet. Okay, here's a good example of supports. You can see here, like this V doesn't really need supports because there's nothing really extreme, but this H here, there's this long bridge that you might need for supports. If it was too long, then the H would start drooping. This T would definitely need supports because there's nothing supporting the ends of the T. Obviously, if you printed them flat, then you wouldn't need supports at all. So that's something that you might want to consider, like print orientation, because that doesn't matter, right? So these were all printed upright, which is why the H and the T needed supports. But if you printed them flat, then it would just be simple 2D profile without supports. Does that make sense? Okay. Also keep it, yeah.
If we do need supports, then we have to add it.
Well, you'll see the program we're going to use to like slice the models can add them automatically. Yeah. But yeah, print orientation is very important. So keep that in mind because again, like the strength in the Z direction is the weakest. So if you're making a mechanical part, like some people CAD bolts, right? And the easiest way to print a bolt is just standing up. But then all the Z axis or all the layers in the Z direction are in the direction that the bolt needs to be the strongest, right? So if you have a 3D printed bolt that's printed this way, and then you bolt something together, and then something pulls it, it's gonna break, right? So there's ways of designing around that, but it's something to keep in mind if you want mechanical components. But yeah, with all of these settings in mind, I'm just gonna teach you how to slice these parts, and then I'm gonna go into more of like the DFM part. So we're gonna download a program called Prusa Slicer. It's a slicer program. There's a bunch of them out there. But yeah, I think I forgot to post the link, but it should be pretty easy to find. Yeah, Prusa Slicer is free, so we're gonna use it. There's a bunch of other free slicers out there. This is one of my favorites. I think if you just type in like Prusa Slicer download, you should get to here. I'm gonna post this. Yeah, you just want to download it. It's a pretty trusted software, so it's not a virus. Yeah, run the installer. I already have it, so I'm just gonna open it up. And I also forgot to post this, so I'm gonna post this as well. No, okay, bruh. Okay, my slicer is not up to date, so it might look slightly different. I'm gonna try to update real quick. Is anyone having trouble downloading the slicer? It should be pretty easy. Yes. Okay. Who hasn't downloaded it yet? If it's waiting, that's fine. Okay. You oh gosh. Come on.
And we download the 3D.
Yeah, we'll do that in a second though. Okay. So who is not at this screen yet? Okay. Okay. Yeah, if once you launch it for the first time, you should be greeted with this. If you're not, then you should just go under printer and then add or remove printer and add or remove presets. Yours should be a lot smaller than this, but I just have a bunch of different presets that I already have configured. So yeah, you shouldn't worry about that. But this takes forever to open. But yeah, you should be greeted with this. You have the opportunity to log in. This is like your Prusa account if you want. I don't have, well, I have one, but I'm just not gonna bother logging in. But if you have a Prusa machine, you can like send files wirelessly. You can skip all of this. Great. But we're gonna be adding a printer shortly once this thing like loads. Would be nice. Okay, cool. You should skip SLA. And you should just do like FFF. You can see it's FFF and not FDM because FDM is like a trademark name. But let's see. I think for on the slides, I'm gonna change this. On the slides, I think it says to use the Mark 4S. But the Mark 4S is like an obsolete model now. So we're just going to go with the Core 1 today. You can see here there's a bunch of different profiles for different machines. Just because every machine's slightly different and some settings are better than others. Some machines are faster than others. So making sure you select the right profile is going to be important. And I just want them all to be the same. So when I grade them, like you should all have the same result as me, or it should be like super close. So please select the same printer I'm using. So I'm selecting the Prusa Core 1 with the high flow 0.4 millimeter nozzle. Yeah, it should be under like Prusa Research and then here. Again, if you closed here, just press finish once you find it, but make sure it's checked. If you accidentally closed it, again, you can, oh great, it's frozen again. You can reopen it by selecting add or remove printers and then add or remove presets. Again, unless you have like a bajillion printers like me, yours shouldn't look like this, and it should just have like one or two. So you want to make sure you're selecting the Prusa Core 1 high flow 0.4 millimeter nozzle. Yeah, your build plate should look like this too. Okay. Raise your hand if you're not there yet. It's okay if you're not. So basically, similar to like Fusion and stuff like that, you have a nice window of your workspace. In this case, it's kind of like a virtual bed. So every 3D printer has like a base plate or a bed that you print off of, and the slicer will have like a model of it, so you can place your parts on it. Obviously, if it's too big, you'll see that like the model will extend past it. But in this case, our model should be pretty small. So today, we're gonna try to slice this 3D Benchy. So if you go to the website I posted, because for some reason 11 megabytes is too big for Discord, you can go to this website and then download the model. Don't download like these G-code files. You want to download the STL file. So the STL, it's like standard tessellation something. It's a 3D model format where all of them or your model is like simplified into a bunch of triangles. I'll explain the difference between STL and STEP in a little bit, but yeah, you want to download this model. And then once you download it, you can insert it into your workspace, and then we can start editing like all the different settings that we want to change. So you can typically do, I think, file, import, and then like STL, step, all that stuff, or just do Control I. You can insert the model, and it should appear like this. Anyone not here? Okay. Yeah, it's kind of fun. I like it original. I'll bring it next week. Okay. So the reason why I'm picking this model is because it's a very popular calibration print. Just because there's so many like minute details in this model that is typically like hard for a printer to reproduce. So again, we're going to be talking about like the DFM stuff, but you'll see here like there's this like pretty steep overhang that your printer needs to overcome. These holes like need to be nice and accurate. There's another like bridge right here that your printer needs to bridge across. These are all like small areas that you need good cooling for. And then like the top, you also need good cooling. So like basically, like kind of the rule of thumb for this is like if your printer can print a good Benchy, then you can typically print like most objects that you're looking to make. There's a bunch of other like calibration like prints out there now because people make them all the time. But this is like the classic one, and I like to print a lot of them. I should have brought them, but I have like a bucket just like full of them because I calibrate my printer all the time. Um, and one of the fun things that people like to do, this is called the speedboat race, and it's basically like print this thing as fast as you can. So like I think the world record right now is under like 2 minutes, which is kind of insane. But before, back in the day when I had like my Prusa Mark III, this thing would take like an hour and a half. Um, so printers are getting quite fast these days. Like sub 30 is like pretty achievable on a lot of machines these days. Um, and you know, I've like shot for like sub 25, like sub 20. I could probably do it, but I keep on breaking my printer. So you'll see later. But hopefully when we have class next week, I'll bring my printer in, which is scary because it's in pieces right now. Anyways, yeah, this is a good model to build off of. We're gonna change a bunch of print settings. It's gonna be like kind of non-ideal for what you normally use the Benchy for. But I just want to go and change them just so you know how all this works. Okay, so let's see. What did we need to change again? So ignore the printer type. We're using the Core 1, but we want to change the perimeters, resolution, infill, and we want to turn supports on. So for perimeters, there's a couple ways you should be able to do it. Oh wait, you'll typically be in beginner mode. So yeah, to change this, you want to go under print settings up here. It'll open like a bunch of different options. You can ignore most of it. You know, the ones that we're after right now is the number of perimeters. Right now it's set to 2, but you can change that to 3. If you change like the mode, like if I change to expert mode real quick, you can see that you get a lot of extra options. As you print more, you might want all of these options available to you, but we're just going to leave it at beginner for now. We want to change the resolution or the layer height to 1.15 millimeters. Okay, we probably should have done that first. But you can see here, there's a bunch of preset profiles that Prusa has made for us. In this case, we want to do 0.15 millimeter speed. So if we click on that, it'll ask us like if we want to transfer some of our settings that we just changed, because changing the perimeters like doesn't migrate to the new profile. So it's like, do you want to transfer it? In this case, yes, we want to keep the 3. So 3. We can change the infill by going on this infill tab and changing the density to, what did I have it as? 20%. So we can change this to 20. There's a bunch of different settings for the pattern. Just leave that alone because that'll affect your time. And then we want to turn supports on. So if we go back, or actually I'll just do support material. If you go to support material and then just click this checkbox, it'll auto-generate the material. You don't need to check this box, just leave it unchecked. But with all those settings applied, you can see if we go back to the platter and we click slice now, it'll apply all those settings to the model for 3D printing. So if we click slice, the computer will think a little bit and it'll create the Okay, so if you did it right, your time should be, under normal mode, it should be like an hour and 6 minutes. Again, I did say like sub 30 is pretty typical, but we did change a bunch of settings that makes it atypical. But yeah. You can see here that the slicer will color code all the different types of toolpaths. So you can see like all this green stuff is like the support material or sacrificial material. Typically for the benchy, you don't print it with supports, but I'm just showing you how to enable the setting for whenever you might need it. The cool thing about these slicers is that you can kind of slide up and down on these bars to see every single layer. So this kind of gives you a good insight on how the machine works. You can see when I drag it to the bottom and I change this slider, you'll see like what the printer does to create your part, right? So this little arrow drawing the line is every single command. Over here on the left is all the G code commands. So like a G1 command is a movement command. I'm just kind of a nerd and I know how to read this, which is kind of sad. But basically, it's just like it's kind of just the 3D printer is kind of stupid and you need to tell it exactly what to do, right? So your computer is smart and it'll program the toolpath, and then your printer is just like, okay, I'll do it. So then it'll just listen to these codes and do it. So you can see it'll draw this perimeter. All this green stuff is like the base of the support material. And once it's finished, you'll see it'll start printing the bottom of the benchy. So you can see there's like a little link at the bottom, nice bottom detail. It'll fill in all these gaps, and then this layer is finished, right? And then it'll keep doing that, slowly building up. You can see here, like we set it at 3 perimeters. So we see this orange is the outer perimeter. These 2 yellow ones are the inner perimeters. You can see the infill starting here, and it slowly builds the part up, right? So if you wanted a good visualization of how this works, the slicer is your friend. But yeah, it's pretty cool. So yeah. Also, something to note, if you ever change any of these settings, like if I wanted to change the amount of infill in this part, you need to reslice the file, right? Because you made a change, it has to recalculate all the toolpaths. So, you know, let's say I wanted this to be like 25%, or I'll make it like really high so you can see the difference. So I made it like 60%. If I slice it again, the printer will think, or not the printer, the computer will think a little bit, generate the G code again, and you can see when I look at it, the inside is a lot denser, right? So again, make sure you're reslicing your stuff whenever you make a change. You can see here, like the print time changed. I think it was like, what, like an hour, 6 minutes before, but now it's like an hour, 11 minutes. So you can see how this could snowball if you have a really large model and you change the infill to be really high. These times will start to shoot up. But yeah, if you're doing it right, you should have the same time as me. For some reason, I think the Mac calculation is a little bit different and it's like off by like 1 minute. If it's 1 minute, then like don't worry about it. But it should be, you should be in like the 1 hour, 6 minute ballpark. If you're not, then one of your settings might be wrong and you might want to go back and look. Yeah. Is anyone's settings or is anyone's time off from this mark?
It's like a whole 10 minutes off.
Minutes? Oh, you could change it to 0.15 speed. Yeah. If you're not using the 0.15 millimeter speed profile, your time is going to be wrong, right? There's multiple like 0.15 profiles, but there are different speeds. So like the balanced and like structural will have different times because they might slow down to make the printer print a little bit stronger. Yeah. Sometimes affect your model. Make sure you select PLA. That's a good point. I forgot to mention that. But
11, but
Now I'm
tell me
wondering.
your height. I changed mine. I don't know. I don't.
Are you using this like
So
0.15?
see, you were showing and then when we changed, like the speed, I changed mine.
Well, like you should change it under this one, this drop down.
So what's your weight?
It's 0.15. It should be point. It should be. You should select this profile, 0.15 speed, because there's two other ones, but they'll output different times. It's 0.15. Yeah, but again, you want to use this profile because. Okay. Yeah. It should be 0.15.
Yes.
Yeah. Sometimes if you run like the PTG profile, it should be a little bit slower. The PTG prints slightly slower.
Like you look at the rate.
Yeah, even here earlier, make sure you're running up to the rate profile because the materials.
So I have a function. So I'm going to formula it and it literally calculates the series for a value of n, and then like the n plus equals one. So it keeps iterating through. But then when the sum result, because like the more sums you calculate, like the change in terms of gradually like like if you print the same if the same term is printed 3 times, that's what I'm trying to figure out. I'm trying to do that separately. I can't necessarily. It's easy when it's two. I think I have to create two. I have to create two.
That's it.
So you should
Actually,
go to 0.2.
I was way back. Actually, that's true.
If the new sum equals the previous sum,
Yeah, same.
I log in. So you need to log it in. I think it's getting harder. It was easy before. Now we just need to memorize it. If we forget this single formula, I mean, math is pretty much equals each time. Oh no.
Yeah.
PTG prints.
I wasn't actually writing down the whole thing. I was like writing all the
Okay, is everyone good on this? I'm assuming if you all submit this, you'll all get 100.
Do we just screenshot that?
Yeah, you just screenshot, make sure I can see the time on the model. But yeah, if your time is like off by a significant margin, I can kind of guess like which ones that you didn't do right. Like if your infill is too high or too low, your time will be wrong. So you should be like within like 1 minute of this. Yeah, that's fine. Okay, no questions?
If I want to make some project that I can get to myself, can I type it on stealth mode?
Stealth mode is just, it makes the printer quieter. Yeah.
It's a better quality.
No, it's just quieter. The machine, it makes the machine quieter. Yeah.
I thought it was to make it stronger.
No, it just makes it quieter. It doesn't really make it that much quieter though.
I thought it was because the parameter is well, there's the 5%. It's the same parameter.
Yeah. Okay. So now that you know how to slice your parts, I'm going to talk about the DFMs part, which is very important for your final. So please listen. Obviously, 3D printing is a very wonderful like type of manufacturing. It's really cheap. It's really fast, relatively speaking. But with any material or with any manufacturing type, there's always some kind of limitation. So I want to talk to you about the 3D printing limitations so you can consider them when you model your finals. So the first big thing is overhangs. So again, we were talking about supports earlier. There's typically like a threshold that you want to start adding supports, right? But if you're designing something, you can design it so that that threshold isn't ever a problem, right? So the general rule of thumb is not to have an overhang over 45 degrees. A lot of printers these days can print steeper overhangs, but 45 degrees is just like a nice number, right? It's in between, it's halfway between 0 and 90, and it's the standard angle of a chamfer. So if you want to just add chamfer to things, you can kind of add them anywhere, and it's nice. So you can see here on the left side, this is a very like shallow overhang. So it's probably closer to like 30 degrees. But as you go farther and farther, this is probably 45. If you go farther and farther, this overhang will become really steep and your printer will have more trouble reproducing it. So you can see here on this model, you can see how like a steep overhang will have like these stair-stepping effect upside down. And if it's too far, it'll stretch out and then it'll droop and then you'll be sad. So make sure 45 degrees, just keep that in mind. Again, if you have questions, just ask me.
Don't have to worry about the base. About the force that we're putting at the end, like the weight being too heavy, even if it's at the right angle.
I mean, that depends on your application, right? If you have something really long and there's a strong weight on the end, you might want to make it thicker. But this is just kind of like general design concepts. So this is relevant in like almost any situation. One situation that I didn't think about when I first started 3D printing was holes. If you think about a hole and you draw like a tangent line along the circle, as you get closer and closer to the top of the circle, you'll eventually get to like flat or like completely 90 degrees, right? That's technically an overhang, right? So when you're printing a hole, like the top end of the hole is going to have an overhang over 45 degrees. And if you're printing a really large hole, that can typically become a problem and you'll start to see the top of the hole sagging. So you can see here, they modeled a hole, but there's this drooping at the top. And depending on how much tolerance you added on this hole, it might make parts fitting together harder, right? So if you made this hole like exactly 3 millimeters and you want a 3 millimeter bolt to go through, this is going to cause a problem and you're going to have to like screw into the plastic. But one of the ways to combat that is by designing the overhang out, right? So you can see here before it's just a round hole, but if you add like this teardrop shape if you think about it, the teardrop, if you model it correctly, is exactly 45 degrees all the way up. So you don't have a steep enough overhang to warrant supports, and it's not going to droop. So you can model these into your parts, and then it'll make fitting a little bit easier. So that's something to keep in mind. Obviously, if your thing needs to be super round, then you can use supports, but you can often get away with these teardrop shapes. Again, this is in the Z direction, right? If you're printing it flat, it can be a circle, but in this vertical direction, you can see these layer lines and you can see that droop. So this is one thing you can think about. You can model these overhangs away. Bridging is what I mentioned earlier about not giving me a Golden Gate bridge. You can see here, like, there are different length bridges on this model. A bridge is just like a span between two different parts of your model with nothing underneath it. You can see for a short bridge, the printer can manage pretty well, right? But as you go longer and longer, you'll see more strands and more drooping. Obviously, if you want a dimensionally accurate model, you don't want it to droop like this. So if you can model these bridges away, then you won't encounter this issue at all, right? Or if you make the bridges small enough, it's typically not as big of an issue. Obviously, if this geometry is necessary for your design, you're going to need supports. But again, you're the designer. If you can design it out, you should probably do so. Yeah, that's bridging. In terms of tolerancing, 3D prints are not perfect models, so you can CAD something to be super, super nice, but when you print it, it's not exactly what you CAD'd it to be. So, I mean, I do extensive tuning to make sure my prints are pretty accurate, but they're not perfect, right? And because of the process of 3D printing, you'll typically have, a slight oversized or undersized depending on what geometry you're looking at. This typically ranges in like the 0.2 to 0.4 millimeter area. I think I'm typically a little bit better than this, but like this range is like something that you want to keep in mind. If you need something more accurate than that, it might be a little bit more difficult. So typically your prints will be slightly oversized. So you might want to compensate for that in your design, right? So like one of the things I do very often, I love M3 screws. So obviously M3 is 3 millimeters in diameter, but if I want to put this thing through a hole, you need to add some clearance, right? So I maybe make the hole like 3.2 millimeters wide. So when I put the bolt in, it'll just slide through without any issue. If I made it just 3, then it'll kind of interfere and I'll have to screw through the plastic or the filament, whatever material I made it out of. So for holes and stuff like that, adding a little bit extra if you want something to fit inside might be something useful. But yeah, typically if you have the printer available to you, you can like print a test and see if it works or not. You kind of have one shot at this because I'm printing your model once. But if you had a 3D printer available to you, you could do a couple iterations to see how tight you could be. The other thing to account for is elephant's foot. Basically, the first couple layers of a 3D print are sometimes squished down a little bit into the build plate just so you can get better bed adhesion. And when that happens, your model kind of gets squished out on the sides. So you can see here, like this zoomed in image, you can see the first 2 layers of this like straight model are bulging out, right? And if you have this tolerance to be important, like if you're fitting something into another piece, this little elephant's foot could cause the pieces to not fit together properly. So one of my recommendations is just adding a chamfer on the bottom of your model. So if you cut like a 45-degree angle here, any amount of elephant's foot, unless it's super, super bad, is just going to be like squished out up to here, and it won't really extend past your model, right? Or extend past this plane that you might want to be nice and straight. right? So I like to add like chamfers to a lot of the bottom of my models whenever I print things, just in case the elephant's foot is a problem. I've tuned out like most of elephant's foot on my printer, but that's something to keep in mind. There's also like compensation, like elephant's foot compensation in like the slicer that you use. So if you have a model without a chamfer on the bottom, you can add a little bit to kind of help. But if you're modeling already, it's typically easier to just add it there. So yeah, that's one thing you can do. Obviously, warping might be an issue. This is typically more on the design or on the printing side, but you can do certain things to your model to prevent warping. Different materials tend to want to warp better or more or less than others. It's becoming less and less of an issue as printers get better. But I used to print with ABS unenclosed, and when that happened, as the material cools, it shrinks a little bit. So the bottom of the the bottom of the print will shrink as the top is still warm, and then it'll curl itself off the print bed, sometimes to the point where it falls off. If the print completes, then sometimes it'll look ugly and sad like this, right? Um, sometimes it's just a skill issue on the person printing. But some of the things you can do to mitigate this is like avoiding sharp corners on the bottom of your print, because those like vertices can be like areas where prints tend to warp more. So if you had this cube and you could like fillet the edges, then rounding out all those corners typically, makes it a little bit easier to print. Again, these are like nitpicky and it's not as big of an issue now, but it's something to keep in mind. If you're like wondering why your print's curling all the time, then like maybe if you can add some fillets, it might help you a little bit. The other thing is if your print is just like takes a large amount of surface area, like if your print is just super wide across the whole bed and it's warping, it's probably because the part is super long. And because it's so long, as it shrinks, the whole part will shrink and then warp, right? So again, if your printer is good, you have good bed adhesion, it may not be an issue, but those are some tips to make your parts more printable. You can have more than one part. I would prefer if your finals were one part, just because I have so many people to print for. But like I've had people like send me like an engine. They're like, "Hey, can you print the engine?" And then like I'll be like, "Okay, sure." Right. So if your design needs more than one part, like I might print it. But I prefer one piece just to make it easier. I don't want to like lose all these things too. Yeah. Do you have any questions about like tolerancing and stuff like that? Because this is pretty like nitpicky, but also pretty important when you design stuff that interfaces with each other. All right, cool. Oh yeah, this is a really good example. So this is a past final from someone who took this class, and they maybe did not pay attention to this tolerancing and thermal expansion part. They made this model of a Lego person, but you can see in the CAD, I don't think they added any tolerance at all. So when they tried to put the torso onto the body, or the legs onto the body, it didn't fit because, this part, the pins were either slightly too big, or like the holes were slightly too small, right? So making sure you add some tolerance if you want interfacing parts is very important, because obviously I don't think this is the result they were after. So yeah, keep that in mind. With that in mind, we have a quiz. I don't think it's a pop quiz because I think it was on the schedule already, but it's a quiz nonetheless. Don't worry too much because you have infinite attempts, and I think it tells you what you got wrong. But this is just, again, just kind of here to make sure you're paying attention today, and keeping all of these design practices and 3D printing things in mind. So feel free to take it now or later. It should be under here. Let me know if anyone is having trouble accessing it. But yeah, today's a short class, so we're like basically done. You don't really have homework this week unless you didn't finish the slicing the benchy thing, and you didn't finish this quiz. But yeah, does anyone have questions about 3D printing and their finals? No. Oh, okay. Wait, due dates. The due date for the final is a week after the last class, which should be next week. So I think it's during October break. So maybe if you were doing stuff during October break, finish it before then. Yeah. Yeah, so there's going to be another Google form for next week, which is where you're going to submit your final. It's just going to be like a screenshot, just like all the other ones. Make sure I can see your timelines. We're going to be doing rendering next week, which is the other part of your final project. And then if you want your final printed, you're going to export the file as a step file, and then it'll be in the Google form as well. Oh yeah, I guess while we're here, I'll talk a little bit about step versus STL. They're both like a 3D file format, but they're slightly different. So again, STL stands for like standard tessellation something. What does it stand for? Oh, wait. Okay, I was wrong. Stereo, I can't pronounce that. But yeah, basically what a STL does is it converts your 3D file into a mesh of a bunch of triangles. So the triangles might be super fine, but it's technically like not your exact model. You can see here, like, I mean, for a face, this might be like kind of worth it just because it's so complex. But for like a cube, it'll simplify your cube into a bunch of triangles. And if you try to edit it in the future, it'll be a really big pain. So that's why I typically recommend everyone export their files in a step format. Because a step file will retain all the curves and geometry that you've created. So like, well, I guess it's kind of hard to see because it just looks like your model. But like a step file will retain like all this curved geometry. So if you like scale or shrink your model, you won't get any like defects. So before, a long time ago, slicers could only read STL files, and I like one time printed this really large like circular shaped object or a cylindrical object, and you could see like the little triangles inside the model, right? But if I was using a step file, then it would still be completely round. So keep that in mind. Step files just typically better. Though some people purposely post STL files because they're really hard to edit. So if you have something that like you don't want people editing for some reason, then like they'll post like STL files because they're a lot harder to edit. Just because like a flat. I mean, I guess some people just do it because they're just, I don't know, annoying. But like, or some people just like forget. But step is better if you want it to be easily editable later. Obviously, you can edit your Fusion file, but if you send a step to someone, they can use another program to edit your file. So I would prefer step files. Obviously, the slicer can read both. The likelihood of me editing your final is probably pretty low, but it typically results in a slightly better finish. But yeah, this is more of a next week thing, but it's just preparing you for that. I have a week to rebuild my printer. This is bad. Okay, it's like pieces right now. But yeah, does anyone have any questions? or questions about the quiz since you're already here? Yeah, it's a long quiz, but it's like open note. So yeah, but yeah, that's all I have for this week. You're free to go. Once everyone's here, I'll start doing my homework. So. No, the trident should be done this weekend.